Direct commanding tone. Consider the physics required to move a metallic mass and stop it at a precise coordinate. Now, tighten that target coordinate to 0.25 nanometers, a distance smaller than a single silicon atom. Finally, execute that exact movement while accelerating the mass at 7G. This specific sequence of physical extremes operates continuously inside the extreme ultraviolet lithography scanners built by ASML. Executing this maneuver requires a machine constructed from over 100,000 discrete components, operating perfectly in unison, at a unit cost of $200 million. The modern computing ecosystem relies entirely on this specific monolithic European architecture. Every advanced AI processor, a laptop CPU, and smartphone chip depends on this exact process to print nanometer-scale circuitry. Operating at this scale often invites comparisons to quantum physics, but the sub-nanometer precision of the EUV machine relies on a different discipline. It is the result of taking classical control engineering mathematics and pushing it to its absolute physical limits. To understand how this system maintains stability under these constraints, we need to construct its mathematical model from the ground up, starting with a mechanical plant that wants to tear itself apart. The production capacity of the digital economy is strictly bound by our ability to calculate and control mass and acceleration in closed loops. The core mechanical plant of the lithography process is the wafer stage, a physical mass suspended above its track entirely by magnetic levitation. To model this, we define our primary unconstrained variables: the mass of the stage itself, represented by the variable m, and the force constant of the magnetic actuator pushing it, represented by k. When we map this to the S-domain to create our baseline mathematical transfer function, we get g of s equals k, divided by m times s squared. That s squared term in the denominator defines the system as a double integrator. If we apply a constant, uncompensated force to an open-loop double integrator, the mass will accelerate continuously. In physical terms, the magnetic levitation system would apply unbounded acceleration to the 7G mass until the stage violently crashed into the boundaries of the machine. Achieving a 0.25 nanometer accuracy requires us to first prevent the machine from destroying itself. Feedback control is a strict physical necessity here to maintain the mechanical integrity of the plant. We close the loop with a controller and negative feedback. This allows the wafer stage to execute the exact start and stop motion required for lithography, known as the step and scan process. The EUV machine must process 275 silicon wafers every hour. To hit that throughput constraint, the controller's rise time must force the stage to reach peak velocity in a matter of milliseconds. This chart maps the system's time response constraints. The stage must violently accelerate, then decelerate, and satisfy its settling time, locking into a strict error band of plus or minus 0.25 nanometers in nanoseconds. If the controller applies too much force, the stage overshoots the target coordinate. At this microscopic scale, a 1% overshoot translates physically into an overlay error, where the printed circuit grid fails to align perfectly with the layer beneath it. Modern processors contain upwards of 50 stacked layers. A single overshoot on any layer severs the vertical pathways, rendering the entire silicon die useless. Textbook time response metrics directly dictate commercial viability. Failing a settling time calculation by 1 nanosecond, or allowing a fractional percentage of overshoot, destroys production yield entirely. The controller must execute this exact curve while simultaneously fighting massive internal physical disturbances. Directly above the wafer, a reticle stage holding the circuit blueprint accelerates in the exact opposite direction at 15G. But the absolute limit of system stability comes from the light source itself. A droplet of molten tin falls through a vacuum chamber and is struck by a laser, exploding into extreme ultraviolet plasma. A 40 kilowatt CO2 laser fires 2 precise pulses into 50,000 individual tin droplets every single second. This reaction generates an immense volume of heat that bleeds outward into the surrounding optical cavity. A temperature shift of just a few millikelvins causes the atom-smooth lenses and mirrors guiding the light to physically expand and warp by nanometers. The heat warps the mass and stiffness of the mechanical components. The EUV machine is a time-varying plant. The mathematical variables of the system are dynamically changing while the machine is running. Guaranteeing bounded input, bounded output stability requires the control loops to actively fight the laws of thermodynamics in real time. The architecture dynamically compensates for the system's own continuous, self-destructive heat generation thousands of times a second. To maintain exact positioning under these conditions, ASML engineers aggressively tune standard proportional integral derivative controllers. The proportional gain is pushed extremely high to guarantee rapid, sub-nanometer responsiveness to positional errors. The derivative gain is scaled massively to act as a dampener against the violent 7G acceleration, cutting off the kinetic energy exactly in time to prevent overlay-destroying overshoot. The integral action continuously sweeps up the remaining microscopic steady-state errors, pulling the stage precisely into that 0.25 nanometer threshold. But waiting for an error to occur and reacting to it is still mathematically too slow for a machine operating at 20,000 Hertz. We must add predictive architecture. A feed-forward loop uses highly complex computational models to calculate the exact physics of the required trajectory ahead of time. It injects the required force directly into the plant before the stage even begins to deviate from its path. The reactive PID loop cleans up the thermal and vibrational variables, while the predictive feed-forward model executes the massive accelerations required for industrial manufacturing speeds. The math we just outlined solves a single axis of motion. Inside the actual cleanroom, the ASML wafer stage is a 6 degree of freedom multi-input, multi-output system. Every single axis is tracked by position sensors accurate to 60 picometers, taking readings 20,000 times a second to feed the closed-loop controllers. That sensor density generates 31 terabytes of raw data per week from a single machine, routed instantly back into the control algorithms. ASML holds a global monopoly on extreme ultraviolet lithography because they are the only organization capable of integrating these specific control loops at scale. The hundreds of billions of dollars allocated by global technology companies to build out the hardware for artificial intelligence strictly require the stability of these physical machines. Transfer functions, time domain constraints, and dynamic control modeling operate at the exact boundary of what physical matter can endure. They are the strict mathematical engine driving the modern technological era.